Have you at any point considered what secrets are concealed in the huge universe? Prestigious American physicist Michio Kaku has made a revelation that vows to change all that. This revelation has been made conceivable by the amazing James Webb Space Telescope. This gadget has uncovered something genuinely progressive. Time as we figure out it doesn't exist. Get ready to set out on a spacetime problem that will shake your impression of the world. The Webb telescope is opening secrets from the farthest corners of the universe, thanks to its advanced infrared technology, turning into a definitive time machine for investigating the past. Join us on this journey to find how this telescope has changed traditional speculations, rethinking how we might interpret time as we know it. If you're keen on staying up with the latest news from the universe and its surroundings, subscribe to our channel, like this video, and turn on the notification bell. Have you ever considered how the astounding resolution and awareness of the Webb Space Telescope make it conceivable to recognize objects of extreme age and faintness, even beyond Hubble's ability? We are referring to far-off galaxies and celestial structures of the early universe, those elusive elements that have been playing an epic grandiose game of find the stowaway. In short, the James Webb Telescope is helping us in the meticulous reconstruction of the vast celestial puzzle of the universe, piece by piece, through its outstanding discovery abilities in the infrared range. Imagine yourself in an art exhibition, perusing moving works captured by the James Webb Space Telescope. These pictures are astounding, with distant worlds sparkling on the astronomical canvas. Among stargazers and cosmologists, there is a sense of astonishment. The typical statement heard is that this is absolutely unforeseen and has shaken the underpinnings of their understanding of the universe. Despite the fact that official reports have not unveiled much about it, the real challenge lies in a recently acknowledged hypothesis, the Big Bang hypothesis. The assumption being questioned is the idea that our universe began through a huge blast a few 13.8 billion years ago and has been expanding like a giant balloon ever since. This hypothesis has been key to how we interpret cosmology for many years. However, groundbreaking observations made by the James Webb Space Telescope have cast doubt on its validity, causing a stir in established science. We can almost imagine Alison Kirkpatrick, a cosmologist at the University of Kansas, questioning her entire career as she lies in bed. Why such a lot of shock? The justification for this bewilderment lies in the fact that galaxies captured by the James Webb don't act according to what the Big Bang theory would predict. They are too small, too uniform, and seem to be of an age inconsistent with this hypothesis. Moreover, their numbers are shockingly high. To address these inconsistencies, we imagine the universe as an expanding globe. According to traditional theory, galaxies shouldn't appear smaller as they move away from us. At some point, they should start to appear larger, as their light would have traveled from when they were closer. This rare but crucial shift in the conceptions of an expanding universe is apparent in the James Webb pictures, where galaxies seem to maintain a similar size to those closer to us. In reality, the traditional theory might be making some mistakes, as astonishing as it may seem. Ongoing research has shown that the Big Bang theory is a mistake in 16 of its predictions, which is a huge number. The only prediction that is precisely confirmed concerns the abundance of deuterium, a type of hydrogen, but that is just the beginning. The theory we have long depended on has also been predicting twice the amount of helium and multiple times the amount of lithium that we actually find in the universe. In addition, the theory of how things came to be faces challenges in trying to explain the colossal structures observed in the universe. According to this hypothesis, these structures are simply too large to have formed since the beginning of the universe. Moreover, the hypothesis struggles to predict the density of matter in the universe. Here comes an intriguing surprise. Those assumed imbalances that were thought not to exist in the cosmic microwave background actually turn out to be real. This adds a surprising twist to the cosmic narrative. This leads us to the James Webb Space Telescope, an astonishing technological achievement that might hold the answers to these vast inconsistencies. These disparities might seem like minor details in the immense landscape of cosmic data we have gathered, but it's important to note that they are far from insignificant. Every little discrepancy adds up to an unaccounted-for part of our cosmic puzzle, preventing the formation of a complete picture of the nature of the universe. These irregularities raise critical questions about everything we thought we knew about the origin and development of the universe. They challenge our understanding of cosmic structure and the very fabric of spacetime, which fundamentally impacts our comprehension of general expansion, gravitational waves, dark matter, and even the ultimate fate of the universe. For instance, if the density of matter turns out to be variable, this would alter our conception of how galaxies are formed and developed, as well as our approach to the role of dark matter in this entire process. Similarly, unexpected errors in the cosmic microwave background could affect our understanding of the initial conditions of the universe and its expansion. These irregularities even have implications for our very understanding of time, as they are closely linked to the evolution of the universe since the Big Bang. If we assume that the theory of how things came to be is not entirely accurate, we would be faced with a need to rethink our view of time, its flow, and its relationship to space. Discoveries of this nature could trigger a paradigm shift in how we interpret spacetime, similar to what happened when Einstein introduced his theory of relativity. We would be on the brink of a new understanding of the universe, in which it would be necessary to recalibrate our cosmic clocks and redefine our coordinates in the universe. Evidently, the universe holds a few surprises in its chest, wouldn't you say? Have you ever puzzled over whether time, as we consider it, is a tangible reality or merely a human construct that we use to observe the past from the present? It is a very complex question, yet we invite you to join us in its exploration. There's a hypothesis that time could be an illusion created by our human memories. According to this hypothesis, everything that has happened or will happen is occurring right now. It is a truly astounding idea, isn't it? If we delve further into this thought, we generally consider time something that flows continuously forward. However, here's the interesting thing. The laws of physics don't require that time works differently if it moves forward or backward. The Big Crunch hypothesis, for example, suggests that when the universe ceases its expansion and begins to contract, time could move in reverse as the universe packs. The temperature would increase like a Big Bang in reverse. Now, what happens after the Big Crunch is a question that has puzzled many of us. Some hypotheses raise the possibility that another universe could emerge from another Big Bang, while others suggest that our universe could return at another point as if there were a cosmic bubble. There are even speculations that the cycle could repeat over and over again, giving rise to endless universes. The captivating idea that time could be bidirectional, that is, that it can flow both forward and backward, has led some researchers to the radical conclusion that time, as we consider it, is really a construct made by humans. They argue that we live in an interconnected spacetime, a concept that finds support in Einstein's theory of relativity. Under this premise, all past, present, and future events occupy their respective coordinates in spacetime, which unfolds in 4 dimensions. So, what does this imply for us? Essentially, it suggests that everything has a reality as solid as the present moment, and that the past and future exist somehow, somewhere in spacetime. MIT physicist Max Tegmark expressed this idea eloquently by describing that we see our reality as a 3-dimensional space where events occur in time, but in reality, it is a 4-dimensional space where everything simply is. If this approach were valid, then time would be revealed as an illusion, as nothing would undergo actual change. Past, present, and future would exist together continuously. These ideas are profound and challenging, yet they are fascinating to contemplate as they illustrate how mysterious and perplexing the universe can be. Julian Barbour, an English physicist, offers a unique perspective on time in our universe. His argument is based on the idea that reality consists of a series of discrete moments, akin to individual photographs in an album, with each picture representing a unique moment. For Barbour, our view of the past is reduced to a construct based on the memory stored in our minds, raising the possibility that the concept of the past is largely an illusion. Barbour addresses this idea throughout his theories of spacetime, where each second exists in a place within a vast landscape that he calls Platonia. In Platonia, each point represents a present, and this landscape is governed by precise mathematical principles that make it inherently timeless. This perspective is associated with the prestigious name of Albert Einstein, whose theory of spacetime is fundamental to our current understanding of the universe. However, the implications of this theory and our understanding of it have raised significant questions. If Einstein's concept of spacetime were to be proven wrong, would it be necessary to discard it entirely in pursuit of a more accurate understanding of the universe? As we delve deeper into the mysteries of the universe, one cannot help but wonder about the intricacies that unfold before us. The study of spacetime, a concept integral to our understanding of the universe, continues to intrigue and challenge the scientific community. At its core, spacetime blends the three dimensions of space with a dimension of time into a single continuum, a framework first conceptualized by Albert Einstein's theory of general relativity. Einstein's groundbreaking theory revolutionized our understanding of gravity, positing that massive objects like planets and stars warp the fabric of spacetime.